Of all the objects in the cosmos,
Planets,
Stars.
galaxies.
none are as strange, mysterious, or powerful as black holes.
Black holes are the most mind-blowing things in the universe.
They could swallow a star completely intact.
Black holes have these powerful jets that just spew matter out.
First discovered on paper,
On the back of an envelope, some squiggles of the pen.
the bizarre solution to a seemingly unsolvable equation,
A mathematical enigma.
Einstein himself could not accept black holes as real.
People didn't even believe for many years that they existed.
Nature doesn't work that way.
Yet slowly, as scientists investigate black holes,
by observing the effect they have on their surroundings.
evidence begins to mount.
That is the proof of a black hole.
Millions of times the mass of the sun.
Cutting-edge discoveries show
We did it.
black holes are very real.
I thought it was crazy.
I said, holy.
But what exactly are they? If we could visit one, what might we see? With their immense power, do black holes somehow shape the very structure of the universe? Is it possible we might not exist without them?
It's quite a journey.
Black Hole Apocalypse, right now on Nova. There are apocalyptic objects in the universe, engines of destruction, menacing and mysterious. Black holes. Even scientists who study them find them astonishing.
Black holes can sort of blow your mind. I'm amazed that these objects actually exist.
Black holes defy our understanding of nature.
Black holes are the greatest mystery in the universe.
They're completely invisible, yet powerful beyond imagining. They can tear a star to shreds.
Black holes actually will eat anything that comes in their path.
You really want to avoid them at all costs.
Black holes even slow time. Once thought too strange to be real, black holes shatter our very understanding of physics. But we're learning they may somehow be necessary for the universe we know to exist.
They might well be the key players in the universe.
What are these strange, powerful objects? Outrageous and surprising. Where are they, and how do they control the universe? The search for black holes is on, and it will be a wild ride across the cosmos to places where everything you think you know is challenged, where space and time, even reality, are stranger than fiction. And we're starting that journey at a very unlikely place. Here, at a remote location in Washington State, where for the first time, a radical new experiment has detected black holes. It originated over 50 years ago, when a few visionary scientists imagined a technology that hasn't yet been invented. Searching for something no one is certain can be found. The experiment is daring and risky. Failure could mark their lives forever. But they don't fail. Right here in these facilities, they make a remarkable discovery. In the early hours of September 14th, 2015, they record a message. It looks and sounds like this. Just a little chirp. But that chirp is epic, monumental. The signal traveled over 1 billion light years to reach us. It started far, far away. And what it tells us is this. Somewhere in the cosmos, over 1 billion years ago, 2 massive black holes circle each other in a fatal encounter. Closer and closer they come, swirling faster and faster, until finally they slam together. The black holes create waves that spread outward, just like vibrations on a drum, a ringing in the fabric of space itself. The collision creates a massive blast, putting out 50 times as much power as the entire visible universe. It sends out a wave not of heat or light or sound, but of gravity.
This gravity wave is moving its way through the universe at the speed of light.
The wave races by stars. On the young Earth, supercontinents are forming. Microscopic organisms have just appeared.
Washing over one galaxy after another, after another.
Dinosaurs roam the Earth.
The wave is still moving.
It zooms through clouds of dust.
And then it nears the Milky Way galaxy.
The Ice Age is just beginning.
We're troglodytes, drawing in caves.
The wave reaches nearby stars. Albert Einstein is in the 6th grade. The wave approaches as close as Alpha Centauri. At midnight on September 13th, 2015, it is as close as Saturn. Finally, over 1 billion years after the black holes collide, the wave reaches us. It strikes a pair of revolutionary new observatories, the sites of the daring experiment. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. The experiment, 50 years in the making, has finally hit the jackpot and opened an entirely new way of exploring the universe. For 400 years, almost everything we've observed in space has come to us in some form of electromagnetic energy. That little chirp is different. What hits the Earth in September 2015 is a gravitational wave, a squeezing and stretching of the very fabric of space. It produced no light. No telescope could ever see the collision. We needed an entirely new kind of observatory to detect it. That wave is new and direct evidence of one of the strangest mysteries in our universe, black holes. Most of us have heard of black holes. They're invisible, powerful.
We're talking about things that are 1 billion times the mass of the sun.
Bizarre. A physical entity with infinite density. No beginning, no end.
They pull things in and warp light. Approach one, and time itself begins to change.
The gravity is so intense that a moving clock will tick slower.
Time will become so slow for you that you will watch the entire future of the universe unfold before your very eyes.
Fall in, and you'd be squeezed as thin as a noodle.
You'll be extruded through the fabric of space and time, like toothpaste through a tube.
Today, we know more about black holes than ever before. But the more we learn, the more mysterious they become.
They're the most exotic objects in the universe. We don't have the physics to describe them.
No matter how well you understand them, they remain unreachable in some sense.
Now, gravity's at maximum. Man is about to enter the black hole.
So black holes have a pretty fierce reputation. And if you want a villain for a sci-fi movie, cast a black hole. But in reality, what exactly is a black hole? And where do they come from? You might think a black hole is like this, an object, but it's not. It's a hole in the fabric of space, a place where there is nothing except gravity, gravity at its most intense and overwhelming.
So if black holes are all about gravity, gravity at its most extreme, what exactly is gravity?
We're all familiar with gravity.
Yep, it's Friday.
It rules our lives. But even so, for a very long time, how gravity actually works was one of the greatest mysteries. Over 300 years ago, Isaac Newton was fascinated with the behavior of moving objects. Eventually, he figured out his laws of motion. They work so well, we still use them today.
We have liftoff at 9:34 a.m.
But Newton's laws can only describe gravity's effects, not explain what it is. And here's where Albert Einstein comes in. Like Newton, he thinks about objects in motion. And he wonders what gravity actually is. Is it a force, or could it be something else? Here's what concerns Einstein. Take this apple. I can't move it without touching it. But if I drop the apple, it moves toward the earth. But what if I take my hand away, and the floor, and the basement, and the floor below that? Then what happens? The apple just keeps falling. Einstein realized that gravity had something to do with falling. Now, if I throw the apple, it falls along a curved path. But imagine I could get the apple moving much faster. Eventually, if I get the apple moving really, really fast, say 17,000 miles an hour, its curved path matches the curve of the Earth. The apple is in orbit, falling freely, just like the International Space Station and the astronauts inside it. According to Einstein, the apple and the space station and the astronauts are all falling freely along a curved path in space. And what makes that path curved? The mass of the Earth.
Einstein came up with a supremely simple concept, and that is that space and time is bent by the Earth and by the sun and by all the objects in the world.
So according to Einstein, the mass of every object causes the space around it to curve.
And that was Einstein's conception. There are no forces anymore. There's just objects bending space-time and other objects following the straightest line through it.
All objects in motion follow the curves in space. So how does the Earth move the apple without touching it? The Earth curves space, and the apple falls freely along those curves. That, according to Einstein's general theory of relativity, is gravity, curved space. And that understanding of gravity, that an object causes the space around it to curve, leads directly to black holes. But it's not Albert Einstein who first makes the connection between gravity and black holes. It's another scientist.
Karl Schwarzschild was a German astronomer head of the Potsdam Observatory in Germany.
Ever since he was a teenager, he had been calculating complicated features of planetary orbits.
As Einstein unveils his theory of gravity in 1915, Karl Schwarzschild is in the German army, calculating artillery trajectories in World War I.
And just weeks after Einstein presented his papers, Schwarzschild, then on the Russian front, quickly got a copy and was mapping the gravitational field around a star.
Einstein had gotten at it through a series of approximations, but Schwarzschild, sitting on the front with bullets and bombs flying, calculated an exact solution to Einstein's theory and sent it to Einstein. Einstein was astonished. He hadn't even imagined that you could solve these equations exactly.
But Schwarzschild isn't done. In his solution to Einstein's equations, he discovers something Einstein himself had not anticipated.
Schwarzschild said, I can calculate this strange distance from a gravitating object that represents a kind of a boundary.
Schwarzschild mathematically concentrates a mass, for example, a star, into a single point. Then he calculates how that mass would bend space and curve rays of light passing nearby.
As he, through his mathematics, aimed particles of light or matter towards this point, there was this boundary surrounding the point at which the particles would just stop. The particles disappeared. Time stopped.
Schwarzschild has discovered that a concentration of mass will warp space to such an extreme that it creates a region of no return. Anything that enters that region will be trapped, unable to escape, even light.
It's like those roach motels. You can check in, but you can't check out. Once you go across that boundary, even if you can sail through, there's nothing you can do to get out. There's nothing you can do to signal out. It becomes this strange cut-off portion of space-time.
What Karl Schwarzschild has discovered is that any mass compressed into a small enough space creates what we today call a black hole. But Albert Einstein, whose own theory of gravity predicts such a thing, cannot believe it can happen in the real world.
Einstein didn't think that nature would act like this.
He didn't like this idea.
Karl Schwarzschild becomes ill and dies before he has a chance to further investigate his own discovery. 2.5 years later, in November 1918, World War I ends. The strange theoretical sphere discovered by Karl Schwarzschild seems destined to be forgotten. Nothing but a curious historical footnote. But in the coming decades, physicists learn more about the atom and about how fusing atoms powers stars, a process called nuclear fusion. Some begin to wonder if something like a black hole could actually come from a star. But not just any star. It would have to be big.
Stars are born in litters, and you get a distribution of sizes and masses. Thousands of little stars, and a few big stars, very big stars, incredibly massive.
Stars are in many ways similar to living creatures. Like humans, they have life cycles.
Investigating stars' life cycles in the 1930s, two visionaries, Subramanian Chandrasekhar and Robert Oppenheimer, discover that the most massive stars end their lives very differently from smaller ones.
The life cycle of a star really depends on its mass. The mass of a star determines what's going to happen after it finishes burning its hydrogen fuel.
All stars start out burning hydrogen, the lightest atom, fusing hydrogen atoms into helium, working their way up to heavier elements. Gravity wants to crush the entire mass of the star, but the enormous energy released by fusion pushes outward, preventing the star from collapsing.
Stars are stable because we have an outward moving pressure due to nuclear fusion, and that's balancing with the inward force of gravity.
Smaller stars can't fuse elements heavier than helium. But in the most massive stars, fusion crushes heavier and heavier atoms, all the way up to iron.
Iron is such a massive element, it has so many protons in it, that by the time you fuse iron, you don't get any energy back out.
Iron is a dead end for stars. Fusing atoms larger than iron doesn't release enough energy to support the star. And without enough energy from fusion keeping the star inflated, there's nothing to fight gravity.
And gravity wins. And so the entire star collapses.
Very rapidly, trillions of tons of material come crashing down, hit the dense core, and bounce back out, blowing off the outer layers of the star in a massive explosion. A supernova. The more mass, the more gravity. So if the remaining core is massive enough, gravity becomes unstoppable.
There's no known force to prevent the collapse to an infinitesimally small dot.
Gravity crushes the stellar core down smaller and smaller and smaller until all its mass is compressed in an infinitely small point. A black hole. The theory makes sense, but most physicists remain skeptical about black holes.
Einstein and Eddington, all the sort of, preeminent astrophysicists in the 1930s through 1950s did not believe that they were actually real. It remained a solution, a mathematical enigma for a very long time. So it took a long time for people to even start looking for them.
It's not until the 1960s that the idea of a supernova creating a black hole is taken seriously. Princeton physicist John Wheeler, who had originally been a skeptic, begins to use a name from history for these invisible objects: black hole.
The term black hole actually originates in India. The black hole was the name of an infamous prison in Calcutta.
Still, no one has ever detected any sign of a black hole. Then in 1967, graduate student Jocelyn Bell discovers a strange, extremely tiny, dead star that gives off very little light. A neutron star. The cold remains of a stellar collapse. The neutron star gives astronomers more confidence that black holes, much heavier dead stars, might also exist. A half-century after Karl Schwarzschild mathematically showed that black holes are theoretically possible, scientists have identified a natural process that might create them: the death of large stars.
So these giant supernova explosions of extremely massive stars make black holes.
Any star that is born with a mass that's about 10 times the mass of the sun or higher will end in a black hole. So our galaxy is replete with little black holes, which are the stellar corpses of generations of stars that have come and gone.
So what are these invisible stellar corpses like? Imagine I'm exploring space with some advanced technology for interstellar travel so that we could visit a black hole, maybe one in our own galactic neighborhood. This particular black hole isn't very big, only about 10 solar masses, meaning 10 times the mass of the sun. And like all black holes, it has an event horizon, a distinct edge to the darkness. That's the boundary Carl Schwarzschild first discovered, where gravity is so strong that nothing can escape, not even light. And that's where we're going. As we get closer, some very strange things begin to happen. Look at the edge of the black hole. See how the image of distant stars is distorted and smeared into a circle? That's gravitational lensing. The black hole's extreme gravity bends the path of light passing by, so that a single point of light, like a star, briefly appears as a ring around the event horizon. I'm now deep in the black hole's gravity well, and we're going to start experiencing the effects. The extreme gravity actually slows down time relative to the Earth. From their point of view, I appear to be slowing down. But from my point of view, time on Earth is speeding up. Now let's say I want to get even closer by taking a spacewalk. The way the black hole slows down time is about to get even more pronounced. To keep track of the changes I'm about to experience, I'm turning on this strobe light. It'll blink once a second. From here, I can see the shadow of the event horizon approaching, and my light blinking normally. But watching from the ship, the closer I move toward the black hole, the more slowly I appear to move. The pulses are nearly infinitely spaced. So it looks as though I'm frozen in time. For me, everything is completely normal, even when I reach the event horizon. If you waited long enough, maybe millions or billions of years, the ship would finally see me disappear. And that's the last you'd see of me. What's inside a black hole? That's still a mystery. And even if I find out, I can never go back and tell you. But I can say this. Black holes may be dark from the outside, but inside they can be bright. I can watch the light from the galaxy that's fallen in behind me, and that's the last thing I'll ever see. Unfortunately, the fun is about to end. Now that I've crossed the event horizon, I'm falling toward the center, where all of the mass of the black hole is concentrated. And I'm beginning to get stretched. As I fall in, the gravitational pull at my feet is stronger than at my head, and my body is starting to get pulled apart. I'll be stretched as long and thin as a noodle, spaghettified. And ultimately, I'll end up completely disintegrating into my fundamental particles, which are then crushed to an infinitely small point. A singularity, where everything we understand about space and time breaks down. Or maybe the black hole, less than 40 miles across on the outside, is as big as a universe on the inside. And as I pass through, my particles will join the primordial soup of a new beginning. So that's what theory tells us we might experience if we could travel to a black hole.
how can we know for sure? How do you investigate something you can't even see?
There are ways to investigate if something is happening somewhere, even if I can't see that thing directly. Take Yankee Stadium. What's happening inside there? Is there a game going on? I can't see the field. I can't see any players or baseballs or bats, but I can definitely tell if there's activity around the park.
It's pretty clear something is going on. It might seem obvious, but whatever it is, I can learn a lot just by observing the happenings around the stadium.
And these do look a lot like baseball fans. And that's the way we investigate black holes, by observing the effect they have on their surroundings.
But what sort of effects? How might a black hole reveal itself? Starting just before World War II, two monumental discoveries are about to radically change astronomy. In 1931, Bell Labs engineer Carl Jansky picks up mysterious radio waves emanating from deep space. Then the sky gets even stranger. When scientists mount Geiger counters on captured German rockets and discover the cosmos is also full of X-rays. These discoveries give astronomers important new tools that will revolutionize the hunt for black holes and dramatically expand our vision.
What our eyes can perceive is a very narrow part of the electromagnetic spectrum.
If the electromagnetic spectrum were laid out along the Brooklyn Bridge, the portion we can see with our eyes would be just a few feet wide. Electromagnetic radiation includes waves of many different frequencies: radio waves, microwaves, infrared and ultraviolet light, X-rays, and gamma rays. Radio and X-ray astronomy open up the sky, revealing dim or even invisible objects, blasting out powerful energy no one knew was there.
They began to realize that this very placid thing that we see out there, all this very quiet thing that looks like nothing is happening and the only thing that's moving is the planets, found out that there was madness going out there. There was chaos out there.
X-rays come from the high energy end of the spectrum. What is creating all this energy? This much is certain. Whatever the source, it is invisible to ordinary telescopes, and it is hot.
X-rays come from things which are at temperatures of millions of degrees, even tens of millions.
One of the first of these X-ray sources to catch the attention of astronomers is named Cygnus X1.
Cygnus, it was in the constellation Cygnus. X, it was an X-ray source. 1, it was the first one he found.
In 1970, Paul Murden is a young English astronomer trying to secure his next job.
I was a research fellow. I was coming to the end of my 3-year contract, and I thought, what can I contribute to finding out what these things are?
Murden works in a 15th century castle surrounded by telescopes, the Royal Observatory. Using the largest telescope in England, he begins searching the area of the constellation Cygnus, the Swan. He decides to hunt for pairs of stars. Pairs of stars are called binaries. They may sound exotic, but they're not at all uncommon. Many of the stars we see, perhaps half, are actually binaries, pairs of orbiting stars locked together by gravity. But Murden wonders, is it possible there are binaries where only one of the stars is visible?
I thought that maybe there was a kind of a star system in which there was a star, one ordinary star that made light, and then there was another star nearby that made X-rays.
The telltale sign of a binary is that the stars are moving around each other. So Murden begins searching for a visible star that shows signs of motion.
Sometimes it's coming towards you, sometimes it's coming away, sometimes it's coming towards you, sometimes it's coming away.
When the star is moving toward us, it appears more blue as the wavelength of its light gets shorter. Moving away, it appears more red as the wavelength of its light gets longer. This is known as Doppler shift. After looking for color changes in hundreds of stars in the area of Cygnus, Murden spots a possible suspect, a visible star whose light is shifting as though moving around.
It very clearly was a binary star, a double star. The star was moving around and around with a period going round once every 5.6 days.
But whatever it's going around can't be seen.
There was no trace in the spectrum of the second star. There was one star there, there wasn't the second star there.
Murden has a binary pair in which only one star is visible. The second object emits X-rays, has enough mass and gravity to dramatically move a star, but gives off no light. Could it be the corpse of a star massive enough to become a black hole?
The crucial issue in deciding whether Cygnus X1 was a black hole was to measure the mass of the X-ray emitting object.
It would have to be very massive, at least 3 times the mass of our sun. If not, it's probably just a neutron star. A collapsed star that's dense, but not heavy enough to be a black hole.
So the observers needed to come up with a conclusion that the dark object, the X-ray emitting object in Cygnus X1, was heavier, hopefully substantially heavier than 3 solar masses.
From his observations, Murden is able to make an estimate of the mass of the invisible partner.
And the answer came out to be 6 times the mass of the sun. So there was a story then that Cygnus X1 was a black hole. And the key to the argument was that the mass of the star you couldn't see was more than 3 solar masses. When I'd finished writing it all out, I sat back and thought, it's a black hole.
This would be the first actual detection of a black hole. It's a huge claim, and Murden will have to convince skeptics, starting with his boss.
The Astronomer Royal, Sir Richard Woolley, he didn't really go for black holes. It's all fanciful. It's kind of, a lot of people in California were talking about this. There are a lot of funny people in California, you know, a lot of hippie-type people.
People like theorist Kip Thorne.
So I was nervous about it. I was nervous about the scale of the discovery, and actually so were other people all around me. I was working with a fellow scientist, Louise Webster, and we were modest about the claim that we were making because we knew what people would think of it. And if you look at the paper we published, it just mentions the word black hole once, right at the end. We think this might be a black hole.
The Paul Murden Louise Webster paper appears in September 1971. Other astronomers agree it could be a black hole, but no one knows for sure. 3 years later, Kip Thorne and the noted British physicist Stephen Hawking make a now famous wager about Cygnus X1.
We made a bet as to whether Cygnus X1 really was a black hole or not.
The bet is partly in jest. Both men hope it is a black hole. But Hawking, not wanting to jinx it, bets against his own wishes.
Stephen claims that Cygnus X1 is not a black hole, and I claim it is a black hole. And so we signed that bet in December 1974. And gradually, the case that it really was a black hole became stronger and stronger and stronger. So in June of 1990, Stephen broke into my office, and he thumbprinted off on this bet, conceded the bet in my absence. I came back from Russia and discovered that he had conceded.
Now, by 1990, the evidence of Cygnus X1's mass may be strong enough to settle a bet between two friends. But the original estimate wasn't precise enough to be definitive. In order to calculate mass, Paul Murden had to rely on rough estimates of the distance to Cygnus X1, which varied by a factor of 10. And the question wouldn't be answered for another 20 years, until astronomer Mark Reed became intrigued by the puzzle. Reed is an astronomer at the Harvard-Smithsonian Center for Astrophysics when he sets out to conclusively prove that Cygnus X1 is a black hole by measuring its precise mass. But how can you measure the mass of an invisible object? Using laws developed by German astronomer Johannes Kepler in the 1600s, it's possible to calculate the mass of a celestial object, but only if you know its distance.
Distance in astronomy is absolutely fundamental. If you don't know distance, you don't know what the object is. Could be a very nearby firefly-like thing. It could be a very distant, huge star, much, much bigger than the sun.
So to get the true, precise mass of Cygnus X1 and confirm that it is a black hole, Reed needs to know how far away it is. But how can he measure the distance to a star? The secret lies in a familiar phenomenon, parallax. It's what our eyes and brains use to see in 3 dimensions.
You can put your finger up at arm's length, look at it, and close one eye. I'm closing my left eye, and I'm looking at my finger relative to the wall in the background there. And now if I open my eye and close my right eye, I see my finger has appeared to move with respect to the original position. And that's because our eyes are separated and we view from different vantage points.
To use parallax to measure distance to an object in the sky, astronomers let the motion of the Earth provide the 2 different vantage points.
Imagine Cygnus X1 is right here, and the Earth and the Sun are over there. Now, the Earth goes around the Sun once a year. And in the springtime, the Earth ends up on one side of the Sun, and we observe Cygnus X1 along a ray path like this. And 6 months later, the Earth goes around the Sun to the other side. We get a different vantage point from Cygnus X1.
Now he has a triangle that goes between the Earth at its 2 positions and Cygnus X1. We know the base of the triangle, the diameter of Earth's orbit. And the principles of geometry tell us that all we need to calculate the distance is the size of the angle at the top.
And we measure this very small angle here at the point at Cygnus X1. And then from direct geometry, we can calculate the distance to Cygnus X1, and from that infer a very accurate mass.
The concept is simple, but Cygnus X1 is so far away that the angle to be measured is minuscule, a tiny fraction of 1 degree. It's smaller than the angle spanned by Abraham Lincoln's nose on a penny in San Francisco, viewed from New York. Because the angle is so very tiny, it can't be measured by any one telescope. But Reed's team has a solution.
We take 10 radio telescopes that are spread across the continental US and to Hawaii and to St. Croix in the Virgin Islands. We use these telescopes simultaneously, and we synthesize in a computer a telescope that has the diameter of the size of the Earth. That gives you incredible angular resolution.
Using this technique, Reed's team determines that Cygnus X1 is 6,000 light years away.
With the new distance we got, the 6,000 light-year distance, we were able to determine that the mass is about 15 solar masses, easily a black hole.
40 years after it was identified as a possibility, Cygnus X1 is now widely accepted as the first confirmed black hole.
It's an understated paper, and the fact that my name was on it and Louise Webster's was on it did us a lot of good in our careers. I think as a result of this discovery, I got offered a permanent job, and it was a great celebration for the family. So it worked out very well for me, as well as getting the intellectual satisfaction of solving a problem.
So finally, after years of speculation, we have a real black hole. Not only that, but a black hole that's blasting out X-rays and has a companion star. If we could visit in my imaginary spaceship, what would we see? The distance to Cygnus X1 has been established at 6,000 light years from Earth. And its mass is 15 solar masses, or 15 times the mass of the sun. And Cygnus X1 is surrounded by an accretion disk, a disk-shaped cloud of gas and dust outside its event horizon, the point of no return. As gravity pulls matter toward the black hole, the cloud starts rotating, just like water being pulled down a drain. Within that accretion disk, particles closest to the black hole whip around at half the speed of light. It's like a giant particle accelerator in space. But why does it emit X-rays? As those particles race around, they collide, which heats them up to millions of degrees. When they get that hot, particles blast out X-rays. And it's those X-rays that first led astronomer Paul Murden to investigate this black hole nearly 5 decades ago. And there's something else about Cygnus that's different. It has a companion star. This blue supergiant star orbits the black hole once every 5.6 days. It orbits so close to Cygnus X1 that the black hole strips material off the star and pulls it into the accretion disk. Some of that material will cross the event horizon and get swallowed up, but not all of it.
Some of the stuff actually comes back out before ever entering the black hole. Kind of like a toddler eating. Half the pasta ends up on the floor, half of it maybe on the ceiling, and some of it in the mouth.
One of the most striking and enigmatic features of Cygnus X1 is its enormous jets. These beams of particles and radiation stream outward from Cygnus's north and south poles, perpendicular to the accretion disk. There's still a lot we don't know about these jets, but they are tightly focused and extremely powerful, blasting out at nearly the speed of light and extending well beyond Cygnus.
When gas gets to these high temperatures and produces the light, there's also a little bit of a magnetic field that forms around them. And we don't understand exactly how, but these magnetic fields help collimate these massive outflows from black holes. Powerful hoses, if you will, that just spew matter out.
So that's Cygnus X1, if we could see it up close. A growing, feeding black hole with huge jets blasting particles way out into the universe.
They're almost these breathing, fire-eating demons, if you will. They flicker, they have bursts. It's a very violent fireball, very active.
What was once a bizarre mathematical curiosity has now become quite real. After decades of skepticism, scientists now accept that burned-out corpses of large stars can trap light inside them, warp space and time around them, attract matter, and accelerate it to mind-boggling speeds.
Black holes seem like such a radical idea that we shouldn't accept it. But bit by bit, the evidence for black holes has gotten stronger and stronger. And we've seen these amazing things.
At least 20 black holes have been found in our galaxy. X-ray binaries like Cygnus X1. And there are probably millions more of these massive stellar corpses in our galaxy alone. Still, a stunning surprise awaits. Everything astronomers think they know about black holes, and much of what they believe about the universe itself, will be upended by a shocking discovery. The revelations begin when radio telescope surveys of the sky detect mysterious hot spots emitting radio energy.
They were coming from what looked like stars.
Because these objects resemble stars, but were discovered through radio signals, astronomers name them quasi-stellar radio sources, quasars. But are they stars or not? The first step in investigating them is to figure out what they're made of. To do that, astronomers analyze the electromagnetic energy they emit. Every element has a unique spectral fingerprint. For example, carbon, helium, hydrogen. These lines reveal the chemical makeup of a star. But the spectrum of a quasar turns out to be incomprehensible.
They looked at it and it was gibberish. It didn't look like there were any emissions from elements that they knew.
What are they missing? There has to be a clue somewhere. Finally, in 1963, Caltech astronomer Martin Schmidt finds it, hiding in plain sight. Buried in the quasar spectrum is the fingerprint of hydrogen.
He noticed something familiar, but it was in the wrong place. The fingerprints of hydrogen had been shifted way off to the red.
It was hard to spot because the spectral lines of hydrogen were radically shifted toward the lower frequency end of the spectrum. And that could only mean one thing. The quasar is moving away from us at fantastic speed. But astronomers have never before seen light shifted to such an extreme. Like a familiar sound shifting too low to understand. The light from quasars has shifted to such a degree that hydrogen is unrecognizable. This extreme amount of shift means quasars are racing away from us at blinding speeds. The reason? It's the legacy of an event that occurred almost 14 billion years ago, the Big Bang. The beginning of our universe. And ever since, the universe has been expanding, carrying with it all the objects it contains, including quasars.
No one had ever seen anything moving away at that high speed. This made this object the furthest away thing that had ever been seen, which meant the thing itself had to be so luminous, and you had to account for that.
2 billion light years away, putting out the energy of 1 trillion suns each second. What could possibly create that?
No one had any idea what could be powering these things. Where could all of this energy come from?
If you work out through calculations, it can't be chemical energy. They knew it couldn't be nuclear energy.
There's no way a quasar could be a star. No amount of nuclear fusion could produce that much star power.
The only engine that could possibly put out that much energy is gravity.
Gravity. In everyday life, we can overcome gravity easily. But when concentrated to an extreme by a black hole, gravity is overwhelmingly powerful. A handful of scientists start wondering,
Could quasars perhaps be powered by gravity engines? What if the energy blasting out from quasars is coming from bright accretion disks around black holes?
To produce that kind of energy, that kind of brightness, it has to involve a black hole.
But not just any black hole.
Whatever was the source of the emission from a quasar had to be massive. How massive? Well, millions or billions of times heavier than the sun.
Millions or billions of times heavier than the sun. Cygnus X1 is only 15 times the mass of the sun. The black holes powering quasars are an entirely different category of black hole. Supermassives. And they seem to be located in the centers of galaxies. But what about our own galaxy? Could there be any supermassive black holes closer to home? The center, where any supermassive would be found, lies in the direction of the constellation Sagittarius, the Archer. Now, Sagittarius isn't just any constellation. It's in the direction of the center of our own Milky Way galaxy. But since we live inside the Milky Way, we can't see the galaxy the way a space traveler would. But I can use my trusted imaginary star machine to show us the galaxy from the outside. Our home is a spiral galaxy, hundreds of billions of stars drawn together into a gigantic disk. It's wide, about 100,000 light years across, but it's relatively thin, only about 1,000 light years thick. And the whole spiral slowly rotates. Our solar system is here. And here, 26,000 light years from the Earth, is the center, which we see in the direction of Sagittarius. In this dense center, there are millions of stars and lots of dust and gas. So that's the view of our galaxy from the outside, thanks to my imaginary technology. But since we live inside the Milky Way, when we look towards the center, we're looking through much of our own galaxy, which means it appears to us as a band of stars and dust across the sky, a Milky Way. Deep inside this band of stars and dust, could a supermassive black hole be lurking?
The data that we're getting now. Where is this?
In the 1990s, astronomers grow determined to solve the mystery, to peer through the murky Milky Way and learn what, if anything, is at its center. One of them is Andrea Ghez.
1 in 20.
Ghez takes on a daunting challenge. She will try to track individual stars orbiting the center of the galaxy.
The essence of this experiment comes from watching stars orbit the center of the galaxy. So you want to find the stars that are as close to the center of the galaxy as possible, which means that I want to get access to the largest telescope I can possibly get my hands on.
And that means coming here. The summit of Mauna Kea, a dormant volcano almost 14,000 feet above the beaches of Hawaii. High altitude and low humidity make this the ideal place for astronomy. The instrument Ghez uses is Mauna Kea's Keck Observatory, one of the largest in the world. But despite its size, Keck has the same problem as all telescopes on Earth: atmospheric distortion.
Think about looking at a pebble at the bottom of a river. The river is moving very quickly, and your view of that pebble is distorted.
Like a river, the Earth's atmosphere is constantly changing, bending light like a funhouse mirror. To compensate for this, Keck pioneers the scientific use of a declassified military technology called adaptive optics. First,
They shine a laser into the sky, creating an artificial guide star. The turbulent atmosphere distorts the guide star. But the computer knows what it should look like and adjusts the telescope mirror accordingly.
So if you look at yourself in a Circus Funhouse mirror, you look completely distorted. And the goal of the adaptive optics system is to introduce a second mirror that's the exact opposite shape and make you look flat again.
Buried deep inside the telescope, the deformable mirror changes shape up to 2,000 times a second to reverse the atmosphere's distortion.
And it has allowed us to take the sharpest images ever obtained of the center of the galaxy.
The sharpness of those images allows Gez to make out individual stars near the center, a huge advance in astronomy. She begins recording their positions in 1995.
And every year since then, we've taken an image. Just take a picture.
Putting those annual snapshots together creates a time-lapse movie of stellar orbits. And what those movies reveal is astounding. The stars are whipping around the center of the Milky Way at phenomenal speeds.
These things are moving at several thousand, up to 10,000 kilometers per second, or 10 million miles per hour. They're really hauling.
To go that fast, the stars must be orbiting something extremely massive.
The mass that we infer is 4 million times the mass of the sun.
What could be 4 million times the mass of the sun, yet be completely invisible?
That is the proof of a black hole.
And not just any black hole, a supermassive, silent and sleeping, right in the center of our own galaxy.
In fact, this is the best evidence to date that we have for the existence of supermassive black holes, not only in the center of our own galaxy, but anywhere in the universe.
A supermassive black hole, 4 million times the mass of the sun, in the very center of our own Milky Way galaxy. From a cosmic perspective, it's right next door. And it raises a profound question. There are billions of galaxies out there. If ours has a supermassive black hole at its center, and if quasars are found at the centers of their galaxies, what about the others?
Are there black holes at the centers of galaxies? If they are, how common are they? We simply didn't know.
Could astronomers ever hope to find what lurks at the centers of other galaxies, millions of light years away, as Gez did in our Milky Way? It would take another innovation in astronomy to make that possible.
And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, window on the universe.
When the Hubble Space Telescope starts delivering clear images of distant galaxies, a team of astronomers gets to work. They become known as the Nukers because their focus is galactic nuclei, the centers of galaxies. One of them is Todd Lauer.
Step one, we take a picture of the galaxy with the Hubble Space Telescope. It shows us where the stars in the galaxy are. It tells us its structure and exquisite resolution.
The key to finding supermassive black holes is to learn how fast the stars in the galaxy are moving. Galaxies outside our own are much too far away to measure the speed of individual stars. But by analyzing the way light is shifted from blue to red at different points in the galaxy, astronomers can put together an average speed of stars orbiting the center. It's accurate enough to create a replica in a computer.
The second step, where the real work begins, is to try to model the observations. And we actually do that by building models of galaxies in the computer.
It's known as Schwarzschild's method, developed by Princeton astronomer Martin Schwarzschild, son of Karl Schwarzschild, whose mathematics first described the possibility of black holes.
Martin Schwarzschild's trick was he would actually build up a model of the galaxy that not only had where the mass was, but it also had how the stars were moving.
For each galaxy they investigate, the nukers painstakingly build a computer model, and then using trial and error, adjust the parameters of mass and velocity, trying to make the model match the original observations they got from the Hubble.
And we say, let's try a star here, let's try one over here, let's have it go around this way, let's have this one go around that way. And we do this thousands and thousands of times until we build up a library of how stars can orbit in this galaxy. Success is when observations of the model match the observations taken with the Hubble Space Telescope.
But that doesn't happen. The models are missing something.
We try it again and again and again, all with no black hole yet, and say, gee, we really can't get the observations explained by the model.
Only when they add an enormous invisible mass at the galaxy's center does the model match the Hubble observations.
Almost always, we have to put in a black hole at the center. We can't match the observations without a black hole in the model.
Of roughly 36 galaxies that the nukers investigate, virtually all of them require a supermassive black hole. And since then, other observations have made us even more certain that supermassives and galaxies go together.
Every galaxy we've looked for one, we have found a supermassive black hole in its center.
It's a stunning revelation. Supermassives, once an entirely unexpected category of black holes, may be common. Not only at the center of our galaxy, but of all galaxies. Take galaxy M31, also known as the Great Andromeda Galaxy. It's 2.5 million light years away. On a clear night, you can see it from Earth. But even with the Hubble Space Telescope, we can't make out precise details of its center. Still, we're pretty sure there's something extremely massive hiding there. What if we could take a closer look? What if we could visit a galaxy far, far away? As we enter the outer part of Andromeda, we're still too far away to see what's lurking at the center. But we can make out a dense cluster of stars in the core, and that could be a sign that there's a giant black hole nearby. Billions of years ago, it would have been surrounded by gas and stars and other small black holes. The black hole may have powered a quasar, feeding mad and blasting out blinding radiation. Over hundreds of millions of years, it would have consumed all the available gas and the closest stars. These days, it's relatively quiet, but it has some distinctive features we've never seen before. First, it's colossal. If it were dropped in our solar system, Mercury, Venus, Earth, and Mars would all be trapped inside the event horizon. That's big, but it's nothing compared to the sheer mass, 100 million times the mass of the Sun. And the destruction won't end there. Jupiter won't last long. The gravitational field of the supermassive will grab hold and swallow it whole. Eventually, Saturn will suffer the same fate. The outer planets might survive, but in cold and dark orbits. This black hole rotates rapidly, distorting and dragging the fabric of space-time. Like all black holes, the event horizon is completely featureless. Remember, there's nothing there. It's just a boundary that conceals the interior. But the accretion disk can tell us a lot about what's going on. That's the fiery ring of gas and dust around the black hole. Imagine if we could release a swarm of autonomous robots to explore the accretion disk. The disk is spinning at an incredible speed, as much as half the speed of light. If Jupiter moved that fast, it would complete its entire orbit in a few hours. The region around the black hole is a cosmic tornado. Now our swarm is caught in the whirlwind too. They're like tracers, dropped into the storm to map the movement. The middle robot can send us images. It's following the leader like a race car speeding around the track. From here, the extreme warping of space-time around the black hole plays crazy tricks on our eyes. It looks like there's one accretion disk whipping around the equator and another arcing over and under the poles. But that's an illusion. The black hole's extreme gravity bends the path of light emitted behind the black hole and makes it look like the accretion disk is both above and below. There's actually nothing around the poles. It's just the passing light rays. That's gravitational lensing again. Drawing much closer to the event horizon, the gravitational lensing would become so extreme that one of my robots could look straight ahead and eventually see its own back, the light forever trapped in an eternal circle. So that's our tour of the supermassive black hole at the center of the Andromeda Galaxy. Pretty amazing. Also amazing, nothing in the mathematics led scientists to imagine that black holes could get that big. As strange as they are, ordinary stellar mass black holes were at least predicted by theory. Supermassives are a complete surprise.
For the stellar mass black holes, people thought about them from a theoretical perspective, and then we found them observationally. The supermassive black holes, the story has been inverted. We actually found evidence of them observationally first, and now we're working on the theory of how did these things come into being.
We already know that stars can collapse to create ordinary black holes, but supermassives are bigger by many orders of magnitude. Cygnus X1 is 15 times as big as our sun. The supermassive at the center of our Milky Way is 4 million times as big as our sun. The one in the Andromeda Galaxy is 100 million times as big as our sun. And it's not the biggest, not even close. There are supermassives 10, even 20 billion times the mass of our sun. How is it possible to make such gigantic black holes? Could supermassives have come from collapsed stars? That seems very unlikely. We don't know any stars billions of times bigger than the sun.
We know about black holes you might get from a dying star. They have several times the mass of the sun contained within them, but millions of times the mass of the sun. If that's the case, a dying star cannot have possibly made it.
So do these supermassives, millions or even billions of times heavier than the sun, somehow just grow, packing it on like voracious giants?
The wild thing about black holes is that they feed. They're constantly devouring anything that comes within their sphere of influence, so they grow.
But how exactly do they grow? What do they eat, and where do they find it?
We believe that black holes grow by accretion of gas. And the way this works is that you have a lot of gas around in the center of a galaxy, and this gas would then assemble and form an accretion disk.
The accretion disk is made up of hydrogen, helium, and other elements in a gaseous form. The immense gravity of the black hole pulls the gas in toward it. As it swirls around, It orbits closer and closer to the black hole, and the feeding begins.
The stuff in the inner regions would get slowly pulled in, sped up, will reach the event horizon, and then that's it.
Whatever gas crosses the event horizon disappears forever. The black hole has absorbed that material.
So it actually adds to the mass of the black hole.
So this is one way a black hole can grow, gradually nibbling gas and dust. But it's not the only way. Cygnus X1 has been slowly stripping material off a nearby star, a process that will likely go on for thousands or millions of years. But what if a black hole could rip an entire star apart in just a matter of years or even weeks? That would be a very violent event, and a team of space explorers is on the lookout.
Roger, copy.
This
Ready
is
for
the
briefing.
Operations Control Center for a space telescope.
IV 5x5, how many? We show beginning of track at 0330.
The Chandra X-ray Observatory.
Copy, receiving data. Roger, please. 16 minutes, 1-6.
Orbiting up to 86,000 miles above the Earth, Chandra takes high-resolution images of objects that emit X-rays. This is one. A short-lived, extremely violent event called a transient, which fascinates James Guillochon.
Supernovae, the destruction of planets by their host stars. I'm just fascinated with destroying things for science.
James is investigating a mystery discovered by a colleague, Da-Sheng Lin. This blur on James's screen is actually a massive sudden burst of X-ray energy, caught by accident.
This little smudge popped up in the background of this image, and given its great distance, it's actually tremendously bright.
Could it be a black hole caught in the act of being born in the violent collapse of a huge star? A supernova. Perhaps. But the intense radiation released by supernova would only linger for a few months. So how long has this mystery object been blasting out X-rays? To find out, they look at images of that same part of the sky taken at earlier dates. 2015, 2011, 2008, 2005 July, 2005 April. No X-rays detected. But the X-rays are there just 3 months later in July. And the powerful, bright signal has continued for more than 10 years, from July 2005 to the present, far too long to be a supernova. So what could it be? A black hole that's not feeding is quiet and completely dark. It won't show up on any telescope. But a black hole that is feeding is different. When it feeds, it blasts out X-rays. So could this be a black hole that's suddenly begun devouring something big?
What effect will this have on anything that comes near? What would it do to a star that wanders too close? Well, it will flay a star, layer by layer, ultimately devouring the entire star.
Unlike Cygnus X1, this is no mere nibbling. This is a 10-year feeding frenzy. A massive black hole devouring an entire star in a cosmic blink of an eye. It's the result of a chance collision, when an unlucky star wanders too close and the black hole's extreme gravity actually rips it apart.
The gravity from the black hole will progressively get stronger and stronger as the star gets near. And at that point, the star will begin to deform.
It's called tidal disruption. It's similar to the way our moon's gravity easily moves all the world's oceans. The tides caused by a black hole would be billions of times stronger and much more violent.
You have these events where a star could be ripped apart by the black hole. So you would see sort of a plume of light from the last gasp of the material in the star.
But there is a chance for some part of the star to escape, as James illustrates.
As the star is elongated by the black hole's tidal forces, it will essentially be feeding the black hole at the same time as half of it is trying to escape. So everything above this point approximately will have the chance of leaving the galaxy. It's moving that rapidly. And everything below this point will fall back onto the black hole and eventually be consumed by it.
So this is another way for a black hole to gain weight. Unlike the slow, steady nibbling of Cygnus X1, this black hole is devouring most of an entire star in one gulp. But whether a black hole feeds suddenly by swallowing half a star or steadily through accretion, astronomers still face a problem when they try to understand how supermassives got so big. The timing problem. The trouble begins with the very oldest supermassives, quasars, those very bright, very distant, and ancient objects first discovered in the early 1960s.
The conundrum was when we started finding these quasars, very bright quasars, very early on in the universe.
They're giving off so much energy that they have to have very massive, supermassive black holes at their center.
But quasars are extremely far away, which means they're part of the very early universe, which began nearly 14 billion years ago.
Bright quasars, 600 million years after the Big Bang, a fraction of today's age.
And they're enormous.
So billion solar mass black holes, these behemoths, had to be in place when the universe was about 550 million years old.
Now you have a problem because you have to grow something really big, really fast. And you are bumping up against sort of physical limits.
Whether a black hole is nibbling or gulping down its meal, it turns out that accretion, how black holes feed, has a speed limit. Named after English astronomer Arthur Eddington, the Eddington limit will not allow a black hole to feed too fast because of the light blasting out from its own accretion disk.
Light has a pressure. So photons can impart a force on something. We see this in winds from stars. Light is pushing out gas. So there's a limit to how fast you can feed a black hole before its own luminosity quenches its own growth.
So given the speed limit, how did early supermassives, quasars, get so big so fast? Could there be a way to bypass the speed limit entirely?
The problem is still time itself. How do you grow them to 1 billion times the mass of the sun? What are the conditions that you need for that kind of growth?
Some scientists are now asking, what if there's a way to create a black hole that's already much more massive from birth, giving it a head start?
If there was a physical mechanism that would allow you to make a black hole seed, which was much more massive from the get-go, then the timing crunch is not as much of an issue and the growing problem is not as acute.
The answer, some believe, is to create a black hole directly from a cloud of gas, a scenario called direct collapse. It starts with gas clouds made of hydrogen, helium, and other elements, the same raw materials from which stars are born.
The denser clouds will start to collapse under their own gravity. And as they collapse, parts that are more dense will collapse more quickly. And so what happens is the cloud fragments.
Those fragments continue collapsing until the hydrogen atoms within them begin to merge. Nuclear fusion begins and stars are created. But what if a giant gas cloud collapsed without making stars?
We realized that there are a set of physical conditions that would allow you to form a very large gas disk prior to the formation of any stars. So this gas disk starts getting unstable. That would allow the mass to sort of flow into the center very, very rapidly and make a very massive black hole.
It's something we've all seen in nature. From tornadoes to bathtubs, a vortex, but on a supermassive scale.
If you're in a bathtub and you pull the plug out and you see the water flowing in a vortex very fast down to the center, that's exactly what happens.
Direct collapse might be a way to create very large black holes early in the universe from enormous gas clouds, completely skipping the star stage. Because they would be so large already at birth, these direct collapse black holes would have a head start, helping them to quickly grow into the enormous young supermassives we see in the distant universe.
You could potentially have these direct collapse black holes. So black holes whose original masses, seed masses, the initial masses, are about 10,000 to maybe 100,000 times the mass of the sun, and that they form from the get-go with that mass.
Direct collapse may explain how enormous early supermassives got their start. But there's another fundamental question about supermassives. What is their role in the universe? Is their existence just a matter of chance? Or are they connected in some larger way to the very structure of the cosmos? Supermassive black holes don't exist in isolation. They seem to live in partnership with galaxies. Collections of millions, billions, or even trillions of stars bound together by gravity. Galaxies are the fundamental building blocks of our universe. So are the supermassive black holes at their centers somehow fundamental to their very existence?
We now just assume every galaxy, even ones we have yet to confirm, will have a supermassive black hole in their center.
It could be that instead of simply being oddities, that they are a key component to galaxies, a key component to the universe.
We've come in a very short time to realize that they likely inhabit the centers of all the galaxies. And that can really only happen if there's some symbiotic relationship between the evolution of a galaxy and the supermassive black hole in its core.
What could that relationship be? One intriguing clue relates to size.
The bigger the galaxy is, the more massive the black hole appears to be. So these black holes at the center seem to know about their larger scale environment.
So which comes first, the galaxy or the supermassive black hole? It's not that simple. It appears they somehow grow in tandem.
It's hard for one to form first and affect the other. So today, we think that whatever formed one had to form the other as a byproduct of that process, and that there has to be some feedback mechanism between the black hole and the galaxy that keeps the growth of the two in lock sync.
The way galaxies grow is by forming new stars from clouds of hydrogen gas.
Gas is essentially the fuel for star formation, just like gas is the fuel for our cars. And so if you run out of gas, you run out of new stars.
So are supermassive black holes somehow interfering with star formation?
When a black hole is growing, a tremendous amount of energy is being liberated and sent out into the galaxy. And so we think that some of that energy goes to warm up gas. And gas that's too warm will not form stars anymore.
The heat produced by a growing black hole makes it impossible for stars to form nearby.
And so One way that a growing black hole can influence its host galaxy is by quenching the star formation.
In effect, the growth of the supermassive determines whether or not its host galaxy grows or stagnates.
They have a kind of eating phase and then a quiescent phase. So they seem to be involved with the formation of the galaxy in that way, and then stabilizing of the galaxy at the same time.
So these mysterious supermassives may actually control the building of the universe. Not so much by their size, but by the way the energy they generate shapes galaxies.
By mass, if you count up all the black holes in the universe, the tiny ones as well as the supermassive ones, the ultramassive ones, black holes are nothing. However, energetically, how much power the galaxy gets and at what time as it assembles seems to be dictated by the central black hole. So they might well be the key players in the universe.
In the next 2 years, NASA plans to launch the James Webb Space Telescope. Humanity's most powerful telescope ever, the James Webb is designed to look in the infrared, allowing it to see farther back in time than Hubble, getting a look at the first stars and galaxies that formed after the Big Bang. Hopes are high that the James Webb Space Telescope will help solve many of the remaining mysteries about the earliest supermassive black holes.
The James Webb Space Telescope is tuned specifically to observe the early universe when galaxies were being born. That could give us deeper understanding of how you end up with a supermassive black hole in your galaxy to begin with.
Technology is moving really fast, and as a result, we have really fundamental new views of the universe. I think we are really living in a golden era of astronomy.
And the James Webb Space Telescope isn't the only new development that promises to solve some of the mysteries around black holes.
I believe have infrared components.
A group of scientists led by Shep Doeleman is now attempting the impossible: to take a picture of a black hole.
It's interesting that we can say something about the accretion flow near the black hole at all.
And if some of this linear behavior survives, maybe we'll have a way of interpreting it.
The project is called the Event Horizon Telescope.
So it depends on when those...
The basic goal of the Event Horizon Telescope is really to see the unseeable. It's to bring into focus something that science has told us for many, many years is precisely something we can't observe, the black hole.
Their primary target is Sagittarius A star, the supermassive in the center of our Milky Way galaxy. They're using a global network of radio telescopes.
We need good weather at 8 different telescopes all around the world, and that is a tall order.
But if black holes are invisible, what exactly do they hope to photograph?
What we're trying to photograph really is the shadow. So as this gas around the black hole swirls inwards and actually hits the event horizon, it leaves a silhouette, a very well-defined shadow on the surrounding light. So really it should look like a donut with its very well-defined hole. And that's the picture that we are after.
If I convert that into frequencies, I get a 2 pi square there.
The team has conducted their first observing run and is processing the data now.
And you're saying the velocity...
It's hoped that these new technologies will give us an unprecedented view of black holes in our universe. But there is one new technology that is already delivering results. And that brings us back here to LIGO, a key player in the black hole drama, to an idea that took root way ahead of its time: gravitational waves. With general relativity, his theory of gravity, Einstein predicts that when an object moves, it can create ripples in space and time, an actual squeezing and stretching of space itself. One of the holy grails of 20th century physics was to detect these gravitational waves.
That was not easy to do with general relativity because all the effects that you could think of were infinitesimally small, very, very difficult to measure.
The thinking was, if gravitational waves could be measured, it would confirm Einstein's prediction. And there could be an added benefit. It might also prove the existence of black holes and help solve the mystery of how supermassives grow. But how to detect gravitational waves? In 1970, the problem caught the attention of a young experimental physicist, Ray Weiss. Ray had the perfect background to hunt for gravitational waves. For decades, he'd been working with more familiar waves, sound waves.
We were immigrants, we were German Jews, and a lot of our friends were very, very interested in music.
Ray devoted himself to coaxing every subtle nuance he could out of recorded music.
Those records had a terrible problem. When the music was loud, it sounded wonderful. When the music was real quiet and slow, what you heard was this shh, like that, a hissing noise. And that was so annoying.
The lessons he learns trying to eliminate noise in recordings will pay off later when Ray turns his attention to detecting gravitational waves.
You have to understand how a gravitational wave does its dirty work.
As a physics problem, gravitational waves are not unlike sound waves.
Suppose the wave comes from something that is in some way moving and oscillating.
A sound wave compresses and expands air. A gravitational wave compresses and expands space and everything in it.
If a wave came through the Earth, it would cause space to expand momentarily and then contract again. It keeps doing it. It's a thing that goes blip, 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 right along like that.
So how to measure the extremely tiny expansion and contraction of space? Ray's idea was to use light. Send a beam of light from one place to another and measure the time it takes to get there. That's how the exact distance to the moon was calculated, bouncing a laser beam from the Earth off a mirror left behind by Apollo 11 astronauts. From the duration of the round trip, scientists could determine the distance. Ray came up with an ingenious design for an instrument that uses lasers and mirrors to detect the faint expansions and contractions of space that would be caused by a gravitational wave. It's called a laser interferometer. It works by firing a laser into a splitter. Half of the light continues straight ahead towards one mirror, while the other half is sent towards another mirror. The distant mirrors bounce the light beams back, where they rejoin at a photodetector. If the distances the two beams travel are exactly the same, the system is designed so the two beams cancel each other out. The detector sees nothing.
You've set the trap to measure the gravitational wave. Now comes a gravitational wave that's coming, let's say, at this structure.
If a gravitational wave passes through, it briefly changes the length of the arms. The light beams no longer arrive back at the same time to cancel each other out. A gravitational wave hits, light appears at the detector. The trap has sprung.
That's the basic idea. It's a very straightforward measurement.
A clever idea and simple in principle. But the devil and the Nobel Prize lie in the details. The difference in length between the two arms would be tiny beyond imagining.
How tiny? Will take the size of an atom. It's less than that. Go down by a factor of 100,000. That's the nucleus of an atom. It's less than that. It was 100 times below that. So we're talking about really itsy bitsy teeny weeny. I thought it was crazy. I think everybody's initial reaction to the idea was, this is going to be impossible.
In 1973, Kip Thorne puts his skepticism on the record in a classic textbook, doubting it will ever work. But Kip has never heard Ray Weiss explain his plan in detail. And when he does...
We spent the whole night talking. And so I said, no, it's very possible. And within no time at all, 20 minutes, maybe half an hour, Kip was solidly understanding this thing. And he says, yep.
And I ate crow the rest of my career because once I had talked with Ray about it in detail, I decided I would spend a large fraction of the rest of my career helping the experimenters.
But it will take 40 years and enormous sums of money to bring Ray and Kip's vision to reality.
Getting LIGO funded was extremely controversial. Hundreds of millions of dollars to detect a signal that had never been seen before. There were many people who feared that LIGO would suck the money out of the room. And so there was a lot of controversy. What everybody could agree on was this was extremely difficult.
With such a sensitive instrument, one of the biggest challenges is Ray Weiss's old hi-fi nemesis, noise.
Ground motion, the seismic motion of the Earth, acoustics noise, sound, everything would tend to move that mirror.
Turns out, even the emptiness of a total vacuum creates a potentially crippling problem. At subatomic distances, the weird randomness of the quantum world causes a ruckus in the mirrors.
This quantum noise is due to quantum fluctuations. These mirrors are doing what an electron does inside an atom. They're jiggling around.
Exquisite sensitivity, extreme vacuum, hundreds of thousands of electronic circuits. LIGO is one of the most complex instruments in the history of science. And as a final means of eliminating false signals, they build not one, but two complete installations. One in Washington State and another in Louisiana.
And so the LIGO designers did it right. They designed more than one detector, separated from one another by great distances, so that if you detect something in one and not in the other, then, go back and check your electronics. Check to see if it was April Fool's Day and somebody didn't just tweak the knobs.
Early fall 2015. Both locations are operating, but the first official science run has not yet begun. They're still testing. In the early hours of Sunday, September 14th, 2015, a scientist in Louisiana makes a fateful decision.
The one up on...
Robert Schofield has been working all weekend, doing final calibrations.
Alrighty, let's take a spectrum.
He has one last test.
So let's see where this computer is getting its power.
But it's late, and the equipment is not cooperating.
It was about 4 or so in the morning, and we still had about another hour of work to do. And we were like, yeah, things aren't working so well, and I'm really tired. Let's not do this last hour or so of work.
They call it a night, and 40 minutes later, in the silence of their inactivity, they open the door to history. A powerful gravitational wave rumbles through both detectors, Louisiana and Washington. Had Robert Schofield worked 40 more minutes that night, With the instruments in test mode, a signal that had been on its way for 1.3 billion years would never have been recorded.
I like to say, you know, one of my biggest contributions to LIGO has been my laziness that day.
I got an email from somebody here saying, hey, you look at this place on the web. I looked at that and I said, holy.
It was so strong that you could see it by eye in the data. It was too good to be true.
But it was true. In fact, it was loud and surprisingly clear.
And it just sang at you. There was standing out.
The signal lasted less than a second, but in that briefest of moments, it delivered a cosmically profound message more than 1 billion years in the making, proving the existence of black holes.
So what we saw in the signal involved oscillations of the mirrors that were slow at first, became faster and faster and faster. And this was precisely the kind of behavior that you would expect from gravitational waves caused by two black holes going around each other, spiraling together.
Two massive black holes, one 29 times the mass of the sun, the other 36 times the mass of the sun, whipping around each other hundreds of times a second, finally completing their act of mutual destruction by merging, creating a single, larger black hole of 62 solar masses. The violent merger converts some of the mass into an apocalyptic release of energy beyond anything ever before witnessed.
The collision, in effect, creates a veritable storm in the fabric or the shape of space and time. As though you had taken 3 suns, you had annihilated them completely, converted it into gravitational waves. The power was 50 times higher than the output power of all the stars in the universe put together, in a fraction of a second. But the most powerful explosion that humans have ever had any evidence for, with the exception of the Big Bang.
Since that very first signal in September 2015, LIGO has detected several more collisions of black holes. In October 2017, Ray Weiss, Kip Thorne, and LIGO's former director Barry Barish received the Nobel Prize. The LIGO discoveries prove that black holes can merge. One way they can grow bigger quickly.
More and more evidence of these merging black holes tells us there are a lot of these stellar black holes around that they can find each other and merge.
And the discovery opened an entirely new way of observing the universe.
We always thought of astronomy as an observational field where we are looking at radiation. We are seeing things. But this is not radiation. This is something much more fundamental. These are sort of fundamental tremors in space-time itself. We can now hear the universe.
For the first time, astronomers have simultaneously seen and heard a cosmic event. In August 2017, LIGO detected gravitational waves from a collision of 2 neutron stars. Black holes are empty space, but neutron stars are dense, dead stars that can crash together and light up the skies. When telescopes and satellites around the globe pointed in the direction of the sound, the world saw fireworks in an explosive collision and afterglow. Possibly, the collision resulted in the creation of a new black hole.
But unless we observe the formation of a black hole, there is much we will never know. Because so much about black holes is irretrievably out of our reach, we can never know where they came from, what's inside, or their history. But we can imagine their future. The number of black holes in the universe is increasing, and they're getting bigger. Stars collapse, black holes feed and merge, new ones form. Could it be that one day everything will end up inside them and they will rule the universe? Untold trillions upon trillions of years after this happens, and the last bits of matter cross their event horizons, black holes themselves may radiate away and vanish from this reality. Their mysteries are many, and we're just starting to unlock the secrets of these strange, powerful places. But one thing is certain: black holes will continue to intrigue us, tantalize us, and challenge both our science and our imaginations.
This NOVA program is available on DVD. To order, visit shoppbs.org or call 1-800-PLAY-PBS. NOVA is also available for download on iTunes.